In this video I want to talk about how we can go from Boolean equations into their implementations using logic gates. Of course you have seen some examples before, but I want to do it right now in a more systematic and nicer way. So let's just go through one example here. So we have this function y equals a bar b bar c bar plus a b bar c bar plus a b bar c. And let us go through what we know from before on how to implement this. So first we have this term, which is the AND of a bar and b bar and c bar, and we know that we can use a 3-input AND gate to accomplish that. So we have this AND gate that has 3 inputs, and its output is going to be a bar, b bar, c bar. So as for the inputs, we notice that all of these are complements of the variable. So for each one of them we need to have this additional inverter that get the values for each one of the variables and then complements that. So this will be the first term that we have. Then for the next one, again we can use a 3-input AND gate to create a b bar c bar, and again here for some of them we need to have a NOT gate. So a is by itself, so we don't invert it, b we invert it, and c we also invert it too. And then finally we have a b bar c. We have a here, we have b bar here, and then we have c here. And finally what we have is a 3-input OR gate that gets in inputs from the output of these 3-input AND gates and combines them together to create the final value for the function. So if you look closely here, you see that there are some redundancies here. So for example, we have several NOT gates that we can just easily eliminate if we basically reuse some of the signals that we create. So for example, whenever we use A, we can connect this one with this one, so they are basically the same thing, right? Or whenever we want to use B bar, we can all connect them to one signal and then eliminate 2 of these NOT gates, right? This thing becomes a little bit more complicated if we have functions that are not created using all the literals. For example, if we had a b plus a bar b bar c plus, and so on and so forth. As you can see, this one is only using 2 of the variables. This one uses 3 of the variables, right? What if you had some terms that were doing like this, right? So you see, when you have a more complex function, the implementation can be a bit convoluted as well. For now, we want to only focus on the implementations of functions that are either shown in sum of product or product of some form, which, as you can see later on, that they are very consistent in the way that the different terms in the Boolean equation is created. For functions like this, depending on the type of the function, you may choose to implement them differently. But the main goal is to implement these functions with as few gates as possible and with as few sources of confusion as possible. So now let me just do the implementation in a little bit of a different way. So since we are working with a function that, as we can clearly see, we have both the variables themselves and their complements too, it is only natural to create some nodes that are the variables and their complement. So what I do is that I just draw some straight lines, as much straight as I can. So this one is A, which makes this line to be A bar, and I do the same for B as well. So this is B and this one is B bar. This one is C and this one is C bar. So we have B here, we have B bar, we have C, and we have C bar. Now what we have is we have three min terms that are created using 3-input AND gate. So I just put three 3-input AND gates all in parallel at the same level. And now I need to create the terms that each one of these produces. So what I do is that I connect these inputs, the three inputs that I have here, with the appropriate variable or its complement. So the first AND gate connects A bar, B bar, and C bar. So what I do is that I just draw a line like this and I connect it to A bar. Let me just erase this. I do the same for B and a similar way to C. As you can see, there is no connection here. If there is a connection, I show it with a dot, right? I will go through the rules of implementation in a later slide too. Now let's focus on the next term. We have A, B bar, and C. So we have A, we have B bar, and then we have C bar. And then finally, for the last term, we have A, B bar, sorry, it should be B bar. B bar, and then finally we have C. So now that we have created this, we need to find the OR of these three terms. So what I do is that I put a 3-input OR gate and I connect the three inputs to these three outputs individually. And this will be my function y. So as you can see, even though for this simplistic example, the difference between this way of implementation and the previous one is not that significant, but still this is more organized. So if you have a function that has more than 4 or 5 variables, and you have let's say 10, 20, 30 different min terms or max terms, it is much easier and much nicer to implement it this way than doing it gate by gate, right? And this can preserve the logic that we follow to come up with the equations, for example, using sum of product form. If we had a function that was in the product of sum form, all these gates would be OR, and this one become an AND gate. So this one is for a product of sum. The same is true for the product of sum case. But for sum of product, we have first AND gates, and then finally we have one OR gate at the end. And in this slide you will see the previous figure, but much nicer and more consistent. So this is what is called a two-level logic implementation of a Boolean equation. So there are some rules to be applied to these type of implementations. Usually, or generally speaking, the inputs are on the left or on top of the graph. The outputs are usually on the right or the bottom of the graph. And usually the gates flow from left to right. And we always try to use straight wires as much as possible, right? So these are the basic rules for creating an implementation for a Boolean equation using logic gates. There are some other rules as well, especially when we have intersection of wires that we use. So if we have wires that form a T-junction, something like this, right? This T-junction, they are always connected. So even though I didn't put any circle here, since it's a T-junction, we know that it is connected. On the other hand, if we have a dot where several wires cross, that means that all of those wires are connected. So this is the case for this one. So we have two wires that go across each other. Since there is a dot, that signifies that these two wires are connected. Or depending on how you want to define wires, these four wires, you can say they are connected at this point. And finally, if you have wires that are crossing but there is no dot, as you can see here, no dot. So when there is no dot, that means that there is no connection here. So if I quickly go back to this one, for example, this is connected because it's a T-junction. The same is true for this one and this one, right? But this is not connected. This is not connected. Why? Because there are wires crossing, but there is no dot that connects them. And for this example, we don't have any two wires that go across each other and there is a dot, right? So here we only have the two cases. But this is something that you should always keep in mind. So in this video, you got introduced to two-level implementation of Boolean equations. I show you some examples on how you can implement a Boolean equation in sum of product form using some AND gates and one OR gate at the end. A similar approach can be done for product of sum implementation. In that case, we have a few OR gates and one AND gate at the end. And then I showed you what are the basic rules for creating circuit schematics based on Boolean equations.